Hello, everyone. Um, I will present you now the second lecture. And first of all, I would like to apologize for the inconvenience that is caused due to some technical problems. And I hope that everything will work well now. I will recall first some important things what we have seen in the previous lecture. That what we have seen, it's that there is always the position I call it, for example, one-dimensional case x. There is the velocity, and this is, it's only the time derivation of dx dt and the acceleration. And this is d 2x divided by 2 times derivation of the position. That it means we have here, this is the velocity, and we call it v. And this is, it means that we have v, it's only x dot. And this is, we call it the acceleration a. And here it's only the velocity v dot, which is equal to dv divided by dt. And it's only also derivation of 2 times of the position x dot dot. That it means what we have in generals, we can summarize in the table here, and we say starting from position, let's say x, that it means we have the position x, then we get velocity, it's x dot, and there is the acceleration, this is x dot dot. That it means we make here what we call time derivation. In opposite side, there is, let's say, starting from acceleration. In this case, what we have x dot dot, which is a, that it means we have acceleration. Let's say a equal to x dot dot. And we have after this the velocity. And here we have v. And this is, we can say it's only the integral of a dt. And there is the position. This is, we can say, x. It's the integral of a dt, of v dt, and this is can be also said it's double integral of a dt. That it means we have in another case opposite. Let's say here we have time integration. Then we have here in one side the position, then we make the derivation with respect to time. And here, if we have the acceleration, in certain case, we know the acceleration and we need to know the velocity and the position. In this case, we have to make the integral. This is the principal things what we have seen in the slide in the previous lecture and some example. Now we take here to see the rest of the lecture. What we have, it's kind of acceleration dependent on here in a certain case on the position. We have seen this case. For example, that if I return back to the then we had the acceleration which is dependent on distance or the position. In the case, for example, gravitational acceleration depends on the height. In this case, that we have x dot dot, it's equal, which is here depending on the position x, and with x, which depends on time. That it means if we have to use what we call the chain rule of the differential calculus, then we have here by definition x dot dot is only the derivation with respect time of the velocity, and the velocity itself, it's depends here on time, of course. Then it means we have here the x dot, it's depend on the position, and here the position depending on time. Then we get here these rules, integrating from the initial condition for the velocity to the actual velocity, and for the position the same, we integrate from the initial position to the actual position. This is what we know here. We say, to get the relationship between the acceleration, which depend on the position, and the position, which depend, of course, on time. Now, if I return back here, there is the case where for many technical problems, issues that we have, for example, damping element, where the acceleration A, in one-dimensional case, let's say x dot dot, which is a function of linear function of the velocity. And there is the case of the air resistance. For example, we have the acceleration, which is here quadratic with the velocity. Now, if we say that here now the acceleration is depending on the velocity x dot, and x dot depending on x, and x itself is depending on time. That it means that if we use the shell rules in differential equation, then we get here by definition x dot dot acceleration, its time derivation of the velocity. But the velocity also depends on x. Then we have here dx dot over dx multiplied by dx over dt. And then we have this by, we know that dx over dt is only the velocity. That it means that we have dx dot divided by dx, and here we make the derivation of the velocity with respect to position x. And here we have x dot, that it means we make the time derivation of the position with respect, we make the derivation of the position with respect to time. Then we solve that here, for example, for solving for small distance, infinitesimal distance. Then we have here dx at this position here, it's only x dot multiplied by dx dot divided by x dot dot. And of course, as we said here, x dot dot, the acceleration is depends on the velocity. Now, if we integrate from certain position, let's say x0 initial to the actual position xt, then we have here the integral of the x equal to the integral of this ratio here with respect to the velocity now. That it means now the right hand side integral is calculated by inserting the velocity acceleration relationship. That it means that for the case, for example, for damping element, we know that this is a linear relation, and here it's quadratic relationship. That it means here, if we take now this integral, then we get here xt with the bonds minus x0, and here we integrate these terms. If we know now the relationship between the acceleration and the velocity, we can make, we can integrate the right hand side of this relationship. Then we have here, for example, separate calculation of the time-dependent velocity by separation of the variable. In this case, we can make here the derivation x dot dot, which is a relationship with the velocity. Then we have by definition dx dot divided by dt, and we get dt here that we integrate from the initial condition, which is at time 0 at rest, to time t, then we get here the time corresponding to this relation. Now, if we take, for example, this example, where we have here the acceleration, it's equal to minus alpha multiplied by x dot. This is the relation, a linear relation between the acceleration and the velocity. Then if we integrate, we use this relationship here, the previous one. This relationship here, then we get that xt minus x0 from the initial condition, that we have xt minus x0. This is the initial position, and with we replace in the previous equation the relationship between the acceleration and the velocity. We replace here and we integrate with respect to the velocity. Then we have here 1 minus alpha, and we integrate the x dot. That means we have here the position xt is only equal to the initial position x0 minus 1 over alpha, actual velocity minus initial velocity. Then we have also that we said the velocity is time dependent. That means that we have this relation, the previous relation, the second relation, what we have seen in yellow, that it's here the time it's only as function of this relationship. Then we replace x dot dot by its linear relation with the velocity. Then we get here time is 1 over alpha log Neperian of x dot 0, the initial velocity, minus log Neperian of the actual velocity. That means if we decompose now, we get here one known in damping, the velocity with respect to time, which is time dependence, it's only minus x0, the initial velocity, exponential of minus alpha t. Then it means if we know the initial position and initial velocity, then alpha is constant. In this case, that we know the velocity at any time t. And if we insert the relationship with xt, the position, then we get here the following relation with respect to this relationship between the velocity and the time. Now there is a relationship, if we look to the graphically, that it means here, this is the velocity versus the time. This is the initial velocity at time t equal to 0, and we see that here it's decreasing, and we see the position, it's increasing with the time reaching a certain constant here. That it means the speed here or the velocity tends to 0, and the distance approach a constant final value. Now, what we have seen in the majority that we have seen until now, it's either one-dimensional problem, which depends, we said that we have x, or we have seen some into the previous tutorial, S, that it means we have one directional problem. And in this case, we make, if we start from the position, then we make the time derivation and we get the velocity and acceleration. The inverse, if we have the acceleration, we integrate and we get the velocity and then the position. We have seen also for the projectile, for example, there is the case when it depends on x and y axis. That means we have two-dimensional case, and we separate the motion in x and epsilon case. There is simplest case that because the aim of this lecture is to come to the 3D problem. That means we start now here with a 2D problem when we have here the coordinate system x1, x2, and x3, where we have the point P here moving on this path here, and we say this is the S, it's only here the position. That means we use now, if we have polar coordinate system, that it means instead to use, particularly for circular and complicated problems, that it's sometimes more difficult to use the Cartesian coordinate system as it's here. Yeah, to simplify the things is to use what we call either the polar coordinate system for the 2D problem and cylindrical coordinate system for the 3D problem. Now, if we have P here on the path in the space, and the distance is measured from any arbitrary reference point S0. That it means here we start from this point here and we follow the path of this particle P. What we introduce here, we introduce what we call orthogonal basis vector. That is mean instead to use this orthogonal basis vector A1 in the direction x1, A2 for the direction x2, and A3 for the direction A3. What we use? We use here tangent unit vector AT, that it means which is always tangent to the path. Yeah. And this will correspond to the velocity, because we said always that the velocity is tangent to the path. And we have here the normal unit vector, which is perpendicular to AT. And we have also the binormal unit vector, AB. That is means we get here, if I draw this, that is means what we have, let's say, for example, if we have the path like this, if we have any point here, we have ET, this is the tangential basis vector. If we can have here, for example, EN, this is normal to AT, that is means here 90 degrees. And there is EB, which is here, can be outward, that is the vector here, EB, or it's called binormal vector. That is means that it's like we have something like ET, EN, and we have here the vector EB, which is this vector here, AB, it's perpendicular to the plane AT and EN. Now we have here from the origin of the coordinate system, the Cartesian coordinate system, we have from the origin, we have here what we call it the position R, which is position vector. That is means has component in x2 and component in x3. Then we have here the 3 vector. And now, if we look to the motion of this particle with respect to time, here we have in space, let's say, time t plus t and t plus delta t. That is means we have at this position here, t, the particle p, and moves to this position, t plus delta t. That is means that the particle cover certain distance here, delta s. Then we have here the position vector with respect to the origin of the coordinate system. We have r here, which is time dependent, and we have the actual position, for example, at time t plus delta t. What we have r plus delta t. That if we look now to the equation that we use, with the velocity let's say here, the average of the velocity, as it's defined, it's only time derivation of the position. In our case here, it's delta S. If we tend now delta T to 0, that it means we take small motion, then we have by definition ds over dt, and it's only s dot. This is the velocity. The same principle. Then it means that here we have the volume velocity, which is important, and you have to keep it in mind that the velocity is always tangent to the path curve, and therefore parallel to the tangent unit vector. That it means here we have the velocity, which is here the norm or the absolute value of the velocity v multiplied by et. Et, it's only the unit vector, which is called also the tangential unit vector, and the tangential unit vector, as we said, it's always parallel, to the path. That it means at each position we have here et, at this position here we have et, which is tangent, to the path. Now, consideration of any arbitrary reference point, the vector position r, which is dependent, of course, on the position st, that we have the velocity here. It's only time derivation of the position vector. Then we have here r, it's depend on the position s. Then it means that we have here, with respect to the r, which is depending on s, that it means we have dr over ds multiplied by ds over dt. And ds over dt is only s dot. Then what we have, dr has the magnitude ds, and is parallel to the path curve. That is means we have here dr, it's the absolute value of the following vector, and et direction. That is means we have here dr, it's only ds, as by definition we said here. We said that here ds, when we take here as ds, if there is any movement, that is means ds will be only dr, as there is the change here, small change to the position vector, with the distance from this point to this point here. Then we have here this dr, any change, in the position, that is means is only ds. If you are in place, that we get here v, the substitution here, the velocity v, it's only s dot multiplied by the unit vector in tangential direction. This is, as I said, keep it in mind, the velocity vector, it's always tangential to the tangent to the path, and it's only the projection of the distance here s, on this on the direction of the tangential on the position s dot, projected in tangent, the tangential direction, and this is only the velocity. Now, if we have the acceleration, it's completely opposite, that we have here acceleration in path direction. There is what we call the tangential acceleration, and this is, it's only the limit when delta t tends to 0, and by definition, it's only dv over dt. but this, it's the tangential position. Then it means it's only v dot, yeah, which is in the direction, the tangential direction, and it's only double derivation of the position S. Then what we have here, we have second component, which is not only the tangential direction, which is always tangent. Yes, it's following the direction of V, yeah, but there is what we call the normal component. And the normal component, then we say additionally normal acceleration En, which is opposite to the velocity. The velocity, it's always in the tangential direction. Then this one, En, it's also perpendicular to Et. As we said, we have three unit vectors, A, T, E, N, and the binormal one, which is E, B. Then it means that if AT is in the direction of E, K, then we have now the acceleration, the normal acceleration, it's perpendicular to the tangential one. And this is defined by V squared divided by R. Then we have here A is the time derivation of the vector V. And this is by definition, the vector V, we said it's here. By definition, it's the absolute value or the norm of V in the tangential direction. But V is time dependent. Et, we will see it, that V is time dependent, and Et, it's also time dependent. Why? Because it's changing the position and also it's changing the direction. Yeah. And each position we have here, the tangential unit vector depend on time. That's what we have. If we make now the derivation here of this formula, what we get V dot AT. We make this derivation with respect to V, yeah, and then d over dt multiplied by E dot AT dot. Then we have here two terms, and you can see these terms here, this the second term in blue color, it's only the normal acceleration. Then if we time change in tangent unit vector, then we have Et, it depends on the position S, and S itself depends on time. Then we can make here dEt over dt with respect to time. We have dEt over ds and ds over dt. This is ds over dt, it's only the absolute value of the velocity v. Then it means if we substitute, then we get v e dot t, it's only v squared dEt over ds. Then if we can see here now, we have at this position, we have S, and at time t plus delta t, we have S plus ds. Then it means we have here the radius r, which is our case only the position vector r. If we have here circular motion, yeah, we have circle here, for example, this is the center of the circle. Then we have here the angle d alpha from the position t to the position t plus dt. Then we have here Et, which is dependent on S, the unit vector in tangential direction, and we have here Et at the position at the time t plus dt, and this is will give here at the position S plus ds. The same time here we have the perpendicular part, the normal part En, which depends on S at the position S, and we have the unit normal here, H as a position S plus ds. Now, if we look to this, then we have the Et. It's only, this is the change of the unit vector. Then we have its Et at the position S plus ds minus Et at the position S. Then we have the Et, if we make here the norm or the absolute value, then it's only the Et multiplied by the alpha. That it means we have here the Et, we have Et here, and if we take, here it's only the tangent, and as the tangent alpha, tangent d alpha, it's only alpha when we take small angle. You know that it's when you have seen for small angle tending to 0, when you have tangent, that it means that you have tangent alpha, it's sinus alpha, it's only alpha, and sinus cosine alpha, it's only 1. As it's tending to 0, then we get here the tangent of the alpha, it's only the alpha. Then we have the unit vector, the absolute value, it's only 1. Because we call it unit vector, that it means that it's vector, but the absolute value of this vector, it's only 1. Then we get here now the Et, it's only the alpha multiplied by An. This is also, you have to keep it in mind, for the tutorial. Now, if we substitute that we have here dEt over ds, it's only 1 over r, the radius, En, and if we replace here dEt over ds, it's only v time derivation of the unit vector in tangential direction. It gives v squared divided by r, En, and then we get the acceleration here, the tangential one, v dot Et, and there is the second one, which is here the normal acceleration. Then in curved path, normal acceleration exists also for a constant speed. That it means here, if we have the velocity which is constant, as you can see, there is v dot. If v dot, if it's the acceleration is constant, the velocity is constant, that it means there is no tangential acceleration. Because at each position, the tangent one is the same velocity at this point, and then this point here at time t1 and t2. But there is always here this part as it's time independent, and this part here for the velocity for the curved path, circular or curved in general. In this case, there is always the component acceleration in this direction, for example, which depends on the velocity squared divided by the radius. When we take the radius here, r, and we have multiplied by the unit vector in normal direction. Then, as we said, we have here En. We have En, which is normal to Et here in the direction V2, and here we have En, which is normal to the direction of V1 as is tangent to the path. Then it means here, if we make the analogy between the equation of motion in Cartesian and polar coordinate system, then what we have here, we have x, the position, the velocity is time derivation, and the acceleration is the time derivation of the velocity and double the time derivation of the position x. The same here, we have s in the curve path. We have s, the velocity is only time derivation, and the same here, there is only the tangential part. But here, compared to the one in Cartesian system here, and the polar coordinate system, in the second case, there is the tangential one, but there is also the normal one. If we have, for example, uniform motion, where the acceleration tangential one is equal to 0, the velocity is constant, c1, then it means that if we make the integral here, that we have the velocity is constant, c1, and we make the integral of the velocity v, then we get the position s, which is linear with the time. If we look now to the initial condition, let's say time t equal to 0, then we get here the initial velocity, which is constant, and for the time t equal to 0, there is no distance, it's at rest. In this case, that we have r, we have s0, then we get here c2. Then it means that we can make v, it's only constant velocity, the initial velocity, and s, which is v0t plus s0. If we have in opposite uniform acceleration motion, that it means here at, which is constant, it's equal to e0 at time t0. Then we have the velocity, it's only the integral. Yeah, we have this constant of integration c1, and we integrate the velocity, we get the position s with respect to the initial condition at time t equal to 0. Then in this case, we get the following terms. Then if we have now the time-dependent acceleration for curved path, that it means we have here at, it's time-dependent, it's dependent on time. Then if we make the integral now, we have at dt plus constant c1. The same for the position s. The position s now, we make a double integral, yeah, of at. Then we get here, we integrate first time, then we get here plus c1 multiplied by t plus second constant of integration. Now, if we look to et, which depends on s, one moment, yeah, there is some problem here.